Okay. Good afternoon, gang. Looks like everybody is here. Or mostly everybody is here. So I'm going to go ahead and get started with some announcements. There is some stuff that we got to talk about that I certainly wasn't expecting to have to talk about, at least today. Let me close these. Switch to this. This is MAC2311, section 004. And today is the 23rd. No hammy. Yes, you're a very cute puppy, but you cannot steal daddy's breakfast. All right. So, some announcements. As you may recall, our plan right now is to have exam 1 on October 2nd, which is next Friday. So I was going to release the study guide this Friday. You guys have a week to work on the study guide, and then the exam takes place a week from this Friday, which would have been 10/2. But exam 1 cannot be on 10/2. The calendar committee here at Santa Fe College, in their infinite wisdom, decided that Santa Fe needs to be closed on October 2nd because that date is UF's homecoming. UF isn't even closing for that day because COVID is going on and there really isn't much to do in the way of homecoming, so they decided not to close. But for whatever reason, Santa Fe decided to close. So that's where we are. Because this is a hybrid class rather than a fully online class, I am obligated to follow the college's schedule. So we meet at the time the college says we're going to meet, and that includes tests. So instead of having the test on the 2nd, which would be next Friday, we will have the test the following Monday. Which is the 5th. Okay, so everything else is going to stay as close to what we were doing as possible. I'll still drop the study guide this Friday. You can work on the study guide from the moment it opens up until the moment of the test. So you'll have a few extra days to study and work on the study guide. I still recommend sending me your work for the study guide as soon as you can, as soon as you finish it, so that I can give you some meaningful written feedback before the test. And from some perspectives, this is a good thing because you have a little bit more time to study for the test. Correct, Caroline. Yeah, so there's no class next Friday. There's not going to be a test. There's not going to be a lecture. There's not going to be nothing because the college is closed. So the upsides are you get a little bit more time to study. The downside is that next week, I cannot spend the whole week just dragging feet. We can't spend the whole week reviewing. I need to make use of this time that we're losing, that we otherwise would be spending on other stuff. So next week, the plan is this. On Monday of next week, we're going to cover some new material. We're going to cover some stuff that's not on exam 1. And then Wednesday of next week, we'll do a review. And then Monday of next week, during our normal class time, yeah, Grayson, we will have the test. So I'm going to post very detailed instructions, exactly what you need to do for the test to Canvas under an announcement. So don't panic too much about procedures. But yes, the test is going to be Monday, October 5th at 12:30 p.m. It'll take place in Canvas, and you will need to use Honor Lock. So unless you've made other arrangements with me or the DRC, you need to make sure you've got a reliable internet connection and a webcam. And then, yeah, the test will be Monday. Monday, 10/5. That's not next Monday, but the Monday after that at 12:30 p.m. Okay, any questions about this? It's kind of irritating, but it is what it is.
Will you have all of our like recorded lectures posted by then? So if we want to go back, we can rewatch them.
Yep, yeah, and they're all up right now. Every lecture from the beginning of the semester through Monday is up on YouTube right now, and I'll continue doing that, posting them as quickly as I can.
I have a question. Do you normally post like the video like after? Because I noticed that I get the notification like when the next time classes starts.
It depends. So usually there's a queue. I'll show you. There's a queue in YouTube. So what you'll see over here,
Would you put it right away?
Finishes, I go ahead and submit the video to upload to YouTube, but then it takes time to upload and it takes time to process. So I submit the video as soon as I can, and then as soon as it gives me the link to post, I post the link. So sometimes that happens while I'm still sitting here at my desk and I get it up same day. Sometimes it's not finished processing or uploading until I come back the next morning. So sometimes it takes me a day or so, but I do my best to post the link same day.
Gotcha. Thank you.
So a quick thing here. The main reason I can't do it on the day the college is closed, besides being like a little bit unfair to you guys, is because some people will be relying on the college's resources, like borrowing a laptop or using a computer in the library or working with the DRC. So because the college is closed on that day, I can't do any of that. Now, if you do have accommodations through the DRC for a test, you don't necessarily need to go to campus, but you do need to talk to me. We need to have established a testing contract. And then you need to talk to me about the accommodations and how you would like them to be taken care of. If you are registered with the DRC and have testing accommodations, your options are as follows. You can tell me about the accommodations and I can program them into HonorLock. And that way you can just take the test at home or wherever and have the extra time. If you want, you can take the test in person at the DRC. They are doing that now, even though COVID's going on, as long as you wear a mask and you make the arrangements with them 3 days in advance. You can take the test at the DRC on their computer. And in that case, you wouldn't need to use HonorLock. I would give you a password to get around it. The third option is to have the DRC proctor you remotely through Zoom. If you would rather do that than use HonorLock, that's also an option. So if you have accommodations with the DRC, please just shoot me a Canvas message or an email, letting me know exactly what you would like to do, and we can set it up. If you want to do the test in person with the DRC, then you would also need to speak directly to Karma or whomever at the DRC and make those arrangements. All right, so today, I want to talk a little bit more about the product and quotient rules. And then we're also going to talk about derivatives of trig functions. So trigonometric functions are hugely important. And so far this semester, we haven't worked with them a whole lot. But we are going to breach that region today. So I would be happy to work on a few homework problems involving the product and quotient rules before we dig into talking about trig derivatives. Are there any homework problems that you guys have found especially challenging or that you would like to work on? Anything that's had you slamming your head into the wall from homework 5? If so, just go ahead and type the problem number in chat. So 38, I think that's deep into the trig stuff. So we're gonna have to talk about the trig stuff. Oh, we don't even have a problem 38 on this homework, do we? Andrew, is that 38 from homework 4? Okay. All right, we can look at that. We'll get 38 from homework 4 and then number 7 from homework 5. Sure. Oh yeah, normal lines. We haven't talked about normal lines, have we? We'll need to talk about that. Sorry, that slipped past me. I did not notice that in there. So let's come back to homework 4 and look at 38 first. And then we'll come to homework 5 and we'll do 5, 7, and 13. That looks like a good batch of things to get started with. Yeah, okay. So give me a second to write this down, and then I'll switch back to the doc cam. Okay. Where'd you go? There it is. All right. So number 38 from homework 4 looks like this. They ask you to draw a diagram to show that there are two tangent lines to the curve y equals x squared, which pass through this point. And then they want you to find the points of tangency, find the points where those lines are tangent to that curve. So first, let me start with the graph of y equals x squared. We know that that looks like this. And I'll say that the point 0, -9 is down here. Right there. So they say that there should be two tangent lines to this curve that pass through this point. Can everybody see why? You kind of think about what tangent lines to this curve look like. You can see that one of them should come through here. The guy would look something like this. And then there's going to be a symmetric one over here. Something like this. So they want us to find this point and this point, where the tangent line to the graph y equals x squared passes through the point down here, 0, -9. So I'll call this P1 and I'll call this P2. We want to find the points P1 and P2. This is a fun problem. It requires a little bit of critical thinking. It's not super obvious. But if we think carefully about it, we can get there. The formula for a tangent line or I should say a tangent line or any tangent line to y equals x squared has slope coming from the derivative. Y prime here is 2x. And must touch the curve y equals x squared. So this is our first kind of crucial observation. So what's the formula then? The equation of the tangent line to y equals x squared at x equals a. So if I wanted to find the tangent line to this curve at an arbitrary x value, I'll call that a, must have slope to a, because the derivative here is 2x. So if you're at x equals a, then the slope has to be 2a, and pass through the point a comma f of a, which in this case is a comma a squared. Right, so the slope has to be 2a because the derivative is 2x, and you have to go through the point a comma a squared because that's what any point on the graph y equals x squared looks like. If the x value is a, then the y value there is a squared. So then you can construct an arbitrary tangent line, meaning a tangent line without having plugged in a specific number for a, just leaving a as what we'd call a free parameter. Therefore, an arbitrary tangent line to y equals x squared looks like, I'm going to start with my point slope formula for a line. That's y minus y1 equals m times x minus x1. Well, y1, the y value at a point that must be on that line is a squared. The slope of the tangent line has to be 2a, and x1, the x value at that point has to be a. So this is what your general equation for a tangent line to y equals x squared looks like. It's always in that form. This is the tangent line at x equals a. So then the problem asks me to find the points where the tangent line goes through 0, -9. If this line is going to go through this point, then when you plug in 0 for x and -9 for y, you get a true statement here. So forcing this to pass through 0, -9, we find y minus, -9 minus a squared equals 2a times 0 minus a. I just plugged 0 in for x and -9 in for y. All right, take this formula. This is the equation of an arbitrary tangent line. I want to make it go through 0, -9. So I plug in 0 for x and -9 for y. This gives me an equation I can solve for a. So let's do a little simplification. This is -9 minus a squared equals -2a squared. Right? 0 minus a is -a. -a times 2a is -2a squared. Now I can add 2a squared to both sides. Minus a squared plus 2a squared is plus a squared, and this is equal to 0. Now I can add 9 to both sides. So a has to be plus or minus 3. So P1 over here has x coordinate -3, and P2 over here has x coordinate +3. So P1, it's on the graph y equals x squared, and it has x value -3, so that's got to be -3, 9. And P2 has x value 3, and it's on the graph y equals x squared, so that's got to be 3, 9. And that's it. So this is a fun concept problem, and if it's not sunk in all the way from watching this, that's good. I want you to go back and work this problem on your own, and make sure you understand what's going on here. It's very clever.
So for my homework, it was 0, -4. So would it be -2, 4, and then 2, 4?
Maybe. You should go back and run this process. So that's what I was saying. Rather than just trying to change the numbers and plug in your answer, I'd very much encourage you to spend some time cooking up the equation of a tangent line to your curve. It'll look the same as this, but then you plug in whatever your point is for x and y, and then you'll solve for your values of a. We can illustrate this. So I'll stay here for just a second more, but then I'm going to flip over to Desmos. We can illustrate this. Yeah, I'll come back to that in just 1 second, Andrew. So y equals x squared is here. An arbitrary tangent line looks like this, and I'm going to toss in a slider here for a. So you see here the tangent line, and I can move around the point of tangency. I'll add in the point of tangency. Oh, I haven't, yeah, let me call this f of x equals x squared. I can add in the point of tangency, like so. And now you see as I move this around, the tangent line moves with it, right? So what I wanted to do is to find a so that the tangent line passes through the point 0, -9. Zoom out a little bit. Here we go. So I claim that this will happen when a is -3, and there it is, you see it. The point of tangency is up here, and this blue tangent line does go through 0, -9. And also over here at +3. So those are the 2 points you're hunting for. And what you see is that it actually doesn't matter what y value you choose. If you wanted to go through the point 0, -5, or 0, -10, or 0, -15, this is all possible. It just depends on where your tangent line is based. So you take your formula for a tangent line, and then you see for what values of a will this go through the point that they give you. And the way you do that is by plugging in the x and y value of that point and then solving for a. So here was our first point, -3, 9, and here was our second point, +3, 9. And both of those give me a tangent line that goes through this point down here, 0, -9. Cool stuff, right? Okay, we wanted to see the bottom of this sheet again. So that's the process of solving. You take your arbitrary tangent line, which you get from plugging the derivative in here. The derivative of x squared is 2x. So at a, the derivative of x squared is 2a. And you plug in the point a, f of a for x1 and y1. Since your tangent to the graph y equals x squared, that a, f of a will be a, squared. So then you take this guy and you plug in 0 for x, -9 for y, and solve for a. To get the y values at these 2 points, you're just taking these x values and plugging them back into the original. Remember, these points are points on the graph, y equals x squared. So the y value is the square of the x value. Okay, so it's going to take a little bit of work, and I think as you solve this problem, if you spend time sitting down and really thinking about this, drawing that picture and really pondering what those tangent lines are, you'll get there. There will be this like click moment where you're like, oh yeah, that makes sense. And then from there, everything feels very trivial, but you need to spend time thinking about it to get there. Questions on this guy? All right, so you wanted 5 and 13 from homework 5, 7, 5, and 13 from homework 5. Also 13 and 14 from 4. Let me take a quick look at those and see what we got going on there. Is 13 that G of T one? Yeah, we did do this last time. We also did this once before then. You just need to set up the limit. It takes a while. If you don't remember, if you want to see me solve this problem, look at the video from Monday. I solved this problem most recently on Monday. 14 is very similar. I really do want you guys to practice these things, so I don't have a problem doing 14 here, even though I believe we've also done this one. But I'll at least start it for us, okay? So we want to use the limit definition to find little g primed of t using the definition of the derivative, where g of t is 3 over the square root of t. Now we could definitely do this with the power rule, now that we know the power rule, but the problem says to use the definition of the derivative. This is, yeah, this was, so there are a few questions requested from homework 4. I'm knocking those out before we do the homework 5 ones. So this is homework 4, number 14. 13, 14, and 38 from homework 4 requested. 13 I did last time, so I'm not going to go back through that, but we just did 38 and now I'm doing 14. So real quick, you could use the power rule here. Let's just see what that looks like. G of t is 3 over the square root of t. That's the same as 3 times t to the negative 1/2 power. So by the power rule, g primed of t should be 3 times negative 1/2 times negative 1/2 times t to the negative 1/2 minus 1. In other words, this should be negative 3/2 times t to the negative 3/2. So real quick with the power rule. But the point of this and 13 is to practice with the limit definition. It's a long problem when you do it that way. By definition here, little g primed is the limit as h goes to 0, g of t plus h minus g of t all over h, which is the limit as h goes to 0, 3 over the square root of t plus h minus 3 over the square root of t, all divided by h. And then we'll need to have a common denominator. I'm going to write the over h as a 1 over h multiplication out front. That way I don't have to write as much huge fraction stuff. This piece I'll multiply by root t over root t. And this piece I'll multiply by root t plus h over root t plus h. So I'll have 3 root t over root t times root t plus h minus, here I'll multiply by root t plus h over root t plus h. So that'll be 3 times the square root of t plus h over root t times root t plus h. And this is the same as the limit h to 0, 3 root t minus 3 root t plus h over h root t times root t plus h, like this. If you try to send h to 0, the top will be 3 root t minus 3 root t, which is 0, and the bottom will be 0 because you've got this factor of h downstairs. So before I can send h to 0, I got to get rid of this thing. And the trick to doing that is to multiply by the conjugate of the numerator. you can factor a 3 out, and that makes life a little bit easier. I'll pull the 3 all the way out past the limit because it is a constant. We can do that. What's left then is root t minus root t plus h over h root t plus h, all multiplied in the denominator. And then I multiply by the conjugate of the numerator, which is root t plus h. And since I'm multiplying that in the top, I have to multiply that in the bottom, like so. And of course, we remember that fractions are grouping symbols, so everything has to be treated like this. The bottom here is all multiplication, so I don't have to worry about foiling anything there. The only place I actually need to FOIL is in the top. So if 3 lim h to 0, my firsts are root t times root t. That's just t. My inners and outers cancel. I'll have root t times root t plus h for my outers, and negative root t plus h times root t for my inners. So those go away. And then my lasts are minus root t plus h times root t plus h. That's just t plus h. And my downstairs, I have h times the square root of t times the square root of t plus h times parentheses root t plus root t plus h. So foiling the top there is a little bit tricky, but we've done so many of these that hopefully it's starting to get to a place where it feels routine. The firsts, root t times root t, stay. The outers and the inners cancel. And then your lasts are root t plus h times root t plus h, that's t plus h, and they're being subtracted because one is negative, one is positive. So this gives me 3 times the limit as h goes to 0. When you distribute this, you'll have t minus h, so that's minus h over h square root t plus h square root t plus square root t plus h, still downstairs. And we can cancel the h's. So then we have 3 times the limit as h goes to 0, negative 1 over square root t times square root t plus h times square root t plus square root t plus h. And now finally, we can send h to 0 because there is no more factor of h in the denominator giving me trouble. So when I plug in 0 for h, I get root t times, this will be another root t because h is going to 0, times this will be root t plus root t. And that's your answer. Now, can we clean this up? Yes, of course we can. Oh, and I lost my 3. Sorry, the 3 is still here. There we go. So this piece here is 2 square roots of t. So altogether, I'll multiply my 3 on the top. I've got negative 3 over root t times root t is t times root t plus root t is 2 root t. Finally, that's negative 3 over 2, and then you can multiply all this. T times root t is t to the 3/2. And then if you wanted, you could write this as negative 3/2 times t to the negative 3/2, which is what we got when we used the power rule. So calculating derivatives using the limit definition is considerably more work than using the power rule or any of the other rules. But it is something you need to be able to do. This is how we introduce the concept of a derivative. This is the thing that makes sense when you think about tangent lines. This is how you connect the rules to the geometry. So it's important that you're comfy with this process. Also, the algebra here, I mean, the main block for calculus is algebra. And this is one way for me to verify that your algebra skills are where they need to be. Are there any questions about any of these steps? I'll leave this page up for just a second more in case anybody is still writing. But then we're going to move on to the next problem. So I think after this, we're ready to move into homework 5 problems. There we want to see numbers 5, 7, and 13. Last call for questions on this procedure. Remember, there will be a problem, at least one problem on exam 1 where I have you calculate a derivative using the limit definition. Okay then. Let's close this, and pull up homework 5. We're going to start with number 5, and then we'll do 7, 13, and 14. So number 5 asks you to calculate f prime and f double primed in this product, which means you're going to need to use the product rule. So I'll write this down and then I'll move back. Our function is x cubed plus 8 times e to the x. I did, yeah, okay, oh, never mind, sorry, that's an old thing, yeah, yep, okay. So, here's my function. It's clearly a product, right? Like this times this. And there's no way to like multiply everything out and just have a polynomial because this is not a polynomial or any sort of power function. So there's no way to like do some algebra and escape needing to use the product rule here. So there's no reason to multiply this out. You might as well just jump in. I'm going to label this piece as u and this piece as v, and I'll remind you what the product rule says. You do need to remember both the product rule and the quotient rule. The product rule says that u times v all primed is u primed times v plus v primed times u. So you differentiate one at a time. You differentiate this function, leave this guy alone, and then you add that to what you get by differentiating this function and leaving this guy alone. So that tells me then that f primed, my first derivative, should be the derivative of this, which is 3x squared times e to the x, I leave that alone, plus, now I leave u alone, and I differentiate v. The derivative of v primed, is still e to the x, and then u left alone is x cubed plus 8. So that's following this formula.
Can you explain real quick how you got the 3x again? I'm sorry.
3x squared is u primed. If u is x cubed plus 8, x cubed, differentiate using the power rule, differentiates to 3 times x raised to the 3 minus 1. That's 3x to the 2.
Thank you.
And then similarly, v primed here is even easier. V primed, the derivative of e to the x is just e to the x. So this piece is u primed. This piece is v. This piece is v primed. This piece is u. Now we can clean this up. This is, I can factor an e to the x out. And what's left here is 3x squared. And what's left here is plus x cubed plus 8. Or if you wanted to write that polynomial in standard form, that would be e to the x times x cubed plus 3x squared plus 8, like this. And that's really as nice as you could possibly write the first derivative. Everybody comfy with how we get to here? Comfy with this factoring? I factored out e to the x, so that first piece just leaves a 3x squared. And when I factor e to the x out of this, it's just x cubed plus 8 that's left. And 3x squared plus x cubed plus 8 is exactly this. Now we didn't just want the first derivative though, they asked me to calculate f prime and f double prime. F double prime is the derivative of f primed. So I need to take this whole thing and prime it. So again, I'm going to use the product rule. I'll differentiate the e to the x and leave the polynomial alone. And then I'll leave e to the x alone and differentiate the polynomial. And I like to write it out schematically like this with the primes. If you can make it easier to see what to do, it can break it down into smaller steps. The derivative of e to the x is e to the x, so this piece is just that. Plus e to the x times, now the derivative of this polynomial, I can use the power rule. The x cubed will differentiate to 3x squared. This piece becomes this. The 3x squared will differentiate to 6x. And the 8 will differentiate to 0. So that is f double primed. And again, we can factor out an e to the x. So if we want to write this nicely, what would be left from this first piece is x cubed plus 3x squared plus 8. And what would be left from the second piece is 3x squared plus 6x. And then you can combine your like terms. So I've got x cubed, and then 3x squared plus 3x squared is plus 6x squared.
I have a quick question.
Mm-hmm.
How did you get the 6x? I see where you got everything else, but I kind of got lost.
That's coming from the derivative of this piece. So
oh, okay.
down the 2, and the 3 times 2 is 6. And then I reduce.
Oh. Gotcha. Thank you.
Yeah.
And why are we factoring out an e to the x if we're adding the two together?
Well, if I had e to the x times, one thing, how do we say this? E to the x times p plus e to the x times q, it just looks nicer as e to the x times p plus q.
Okay, gotcha.
That's all. So it's just it's a way to write this as nicely as possible. Really, you could stop here, right? This would be a correct answer. But oftentimes when we're working with derivatives, we're going to want to solve an inequality, or we're going to want to set it equal to 0. We're going to want to do something with that derivative down the line. So it's good to get into the habit of trying to write the derivative as nicely as possible. And to do that here, I factor out the e to the x. So then I just get e to the x times some polynomial. It's not necessary for this problem, but it will be necessary when we get to chapter 4. So I'm just trying to introduce that mechanism now. These are great questions. Is there anything else you guys are wondering? Okay, so that was number 5. We wanted to see 7, 13, 7 and 13. So let's take a look at number 7. Here we're talking about normal and tangent lines. Now I haven't talked about a normal line with you, so let me introduce that concept first. It's not important in Calc 1, but the concept of a normal object will be important in Calc 3, so we might as well. The tangent line is the line that has the same slope as f of x at that point, right? It's like the tangent line, if I base my work right here at A, my tangent line looks like this. Right? The normal line is the line through that same point perpendicular to the tangent line. So the point there, as always, is A comma f of A. So the way you'll build the normal line is the same way you build the tangent line. You're going to use the point slope formula. But then you'll use, instead of the derivative to get the equation of the tangent line, you'll take whatever slope you would get for the tangent line and then take its negative reciprocal to get a perpendicular line. Everybody remembers that two lines are perpendicular if and only if their slopes are opposite reciprocals, right? So think of the normal line as the line that points straight out from the graph. Over here, the normal line would look like this. Over here, the normal line would look like this. It's not super duper useful in Calc 1, but when you get to Calc 3 and you're talking about orientable surfaces, or you're imagining objects like moving, this is kind of the idea. The normal line or normal vector points out. So it points in towards the center of curvature on the one side, and on the other side it points out away from the function, perpendicular to the tangent line. So the definition of the normal line is the line passing through A comma f of A, perpendicular to the tangent line. So the slope would be -1 over f primed of A. Because remember, two lines are perpendicular if they have opposite reciprocal slopes. So yeah, Andrew asked me a question here, and I'll share it with you guys. So you're really just looking for the tangent line, then applying the negative reciprocal to find the normal line? Yes, exactly. So it's not really anything new. Only thing new is the vocab, really. Now the function we wanted to work with is 8x e to the x. So this is homework 5, number 7. Find the tangent and normal lines to f of x equals 8x e to the x at 0, 0. Yeah, it's nice that there isn't really any new memorization that's required here beyond the definition. You just got to remember that the normal is perpendicular to the tangent, goes through the same point and is perpendicular to the tangent. So first we need f primed, and that requires the product rule, because this is 8x times e to the x that we're priming. So first I'll differentiate the 8x and leave e to the x alone, and then I'll leave the 8x alone and differentiate e to the x. The derivative of 8x is just 8, so this first piece is 8 e to the x plus the second piece here is 8x times the derivative of e to the x. Well, the derivative of e to the x is still just e to the x. And I would factor as much as you can. So what I can factor here is 8 e to the x. And what's left is going to be 1 plus x. So the slope of the tangent line, I'll call it m tan. That's f primed of 0, because we're working at the point 0, 0, which is 8 times e to the 0 times 1 plus 0. E to the 0 is 1, 1 plus 0 is 1, so this is just 8. And the slope of the normal line, which I'll write as m norm, that would be negative reciprocal of this, so negative 1/8. So the tangent line that's y minus 0 equals 8 times x minus 0, or just y equals 8x. And the normal line is y minus 0 equals negative 1/8 times x minus 0, or just y equals negative 1/8 x. Not too bad. This is, I'm realizing now, hard to read. That's an ampersand. So tangent and normal lines. Okay. So let's take a look at number 13 here. Unless there are any questions on this. Any questions on this guy? So we need the product rule to get started. That's the main thing we're trying to practice in the first part of homework 5, right, is the product and quotient rules. That gives us f prime. To get the slope of the tangent line at x equals 0, we plug x equals 0 into f primed. And to get the slope of the normal line, you just take the negative reciprocal of the slope of the tangent line, because it is perpendicular. They both go through the same point. They both have to go through 0, 0, because they are tangent and normal lines at 0, 0. Just for fun, let's flip over to Desmos for a minute and take a look at that. So this was my function. There's the tangent. And there's the normal. I can rescale my y-axis a little bit. You can see a little bit better what's going on. Maybe that's too much. Something like this, right? So the green is tangent to the red at 0, and this guy is perpendicular. Okay. I won't be bugging you guys too much about normal lines, so don't stress too much. There isn't anything extra you need to learn or remember here, besides that normal lines are perpendicular to tangent lines. But like I said, not an important concept in Calc 1, but will be an important concept in Calc 3. Let's take a look at number 13 next. Ah, this is good. So these problems where things get a little bit abstract are a really good test of your understanding. How well have you comprehended the different formulae? So we want to find, I'll write this down and then find the derivatives of y equals x to the 7 times f of x. So that will be a product rule thing. Y equals f of x over x to the 4. So that will be a quotient rule thing. And y equals x to the 5 over f of x. That will also be a quotient rule thing. And the assumption that f is differentiable just means that f prime exists. That we can write down f prime without worrying about whether or not it exists. So in part A, y primed is the derivative of x to the 7 times f of x. And so following the product rule, here's u, here's v. I'll have x to the 7 primed times f of x plus x to the 7 times f of x primed. The derivative of x to the 7 is 7x to the 6. So this first piece is 7x to the 6 times f of x. And the second piece is x to the 7 times the derivative of f of x. Well, that's just f primed. So that's it, job done. You could factor an x to the 6 out if you wanted. And then you would have 7f of x plus x f primed of x. But you don't need to. Parts B and C are a little bit harder because the quotient rule is a little bit nastier. I'm going to remind you the statement of the quotient rule, and I'm going to put it on a separate sheet here so I don't take up any space that I need. The quotient rule says that u over v, all primed, is v times u primed minus u times v primed all over v squared. That's low d high minus high d low over low low. That's the mnemonic. It's really useful. So the u is high, the v is low, low d high, the bottom times the derivative of the top, minus high d low, the top times the derivative of the bottom, all over the bottom squared. If you get the order wrong in the numerator, the answer will come out negative. So you really do need to make sure you remember this. So following our quotient rule, y primed here would be the low d high, that's x to the 4 times the derivative of the top, which is f primed, minus the top, which is f, times the derivative of the bottom, which is 4x cubed, following the power rule, all over the bottom squared. X to the 4 squared is x to the 8. And again, if you wanted to, you could clean this up a little bit. You could factor an x cubed out, but you don't have to. Similarly, we follow the quotient rule for part C to find here that y primed would be low d high, that's f of x, times the derivative of x to the 5 is 5x to the 4, minus high d low, that's x to the 5, times the derivative of the bottom, which is the derivative of f, or just f primed, all over the bottom squared, which would be f of x all squared. So make sure you remember this. The easy way is to think low d high minus high d low over low low. It's a silly trick, but it works. I don't know why, it just sticks in the brain. All right. So I think that's enough on the product and quotient rules. You should be pretty cozy with them by now. Remember to make sure you're keeping up with the homework, right? The lectures are only going to be as valuable as you make them, meaning you have to be working on the material that we're talking about when we meet. So keep yourself caught up with the homework. That way this will serve to reinforce rather than just, sounding like a bunch of gobbledygook. We need to begin the next section, which is on derivatives of trig functions. If I remember right, this is section, oh shit, I don't even remember, what is this? 3.3, yeah, okay. So section 3.3 is the last section on exam 1. And we're going to begin by trying to find the derivative of sine. And I like the way the textbook does this because they start with a kind of intuitive thing before jumping into the limit. So I will be looking at the limit. There is some complicated stuff in the limit definition of the derivative for sine, but we're going to get there gradually. So I'll mark this as 1, I'll mark this as -1, and I'll mark this as 2 pi. So this halfway is pi. This is pi over 2. And this is 3 pi over 2. And we're just going to graph the sine function. So sine here looks like this. It's about like that, right? I can extend over here. This is negative pi. This is negative pi over 2. So if you look on this graph, let's find the places where the tangent line is horizontal. Let's do this game where you try to sketch the derivative from the graph of the original. Remember, we did a lot of that back in the previous sections in 2.8. Let's do it now. I have a horizontal tangent line here. So the slope here is 0. I have a horizontal tangent line here. So the slope here is 0. I have another one over here. If you look at x equals 0, the slope here looks like it's about 1. And if you look here, the slope looks like it's about negative 1. And if you look here again, you know this continues like this. The slope here looks like it's 1. So this is the graph f of x equals sine x. And then I'm going to try to sketch a graph of his derivative down here, just using the methods from section 2.8. So when x is 0, f prime should be 1. When x is negative pi over 2, x should be, the slope is 0, so f prime there is 0. At positive pi over 2, the slope was 0. At positive pi, the slope was negative 1. At 3 pi over 2, the slope is 0. And at 2 pi, the slope was back up to 1. If I go connecting these points, I get something that looks like this. Who does that look like to you?
Is that cosine?
Yeah, it is, right? This looks just like cosine. It is cosine. So that's our conjecture. We conjecture that the derivative of sine is cosine based on the methods of 2.8. But it's another matter entirely to prove that the derivative of sine is cosine. And that's what I'm going to spend the next 20 or so minutes doing. It's going to take a little bit of work, and I'm going to need you to be very patient and very diligent as we do this, because the argument is geometric. And it's not super straightforward. It requires using some trig identities, a little bit of somewhat complicated algebra, and then finally a geometric argument to resolve a challenging limit. So, theorem. Sine of x primed is cos x. Proof. If f of x equals sine x, then f primed x is the limit as h goes to 0, f of x plus h minus f of x all over h, which, if you plug in the sine function, is limit h to 0 sine of x plus h minus the sine of x all over h. And in order for me to get anywhere with this, I need to be able to expand the sine of x plus h. It is not sine of x plus sine of h. Hopefully We remember that from our trig classes. I know trig at Santa Fe is not awesome, but hopefully we remember at least that much. There is a formula for the sine of a plus b. I'll show it to you on a post-it, and then we're going to use the version of that we need here. So recall, the sine of a plus b is the sine of a times the cos of b plus the sine of b times the cos of a. Everybody remember this? So the sine of x plus h, I'll leave this over here. The sine of x plus h is the sine of x times the cos of h plus the sine of h times the cos of x. That's just this piece. That is this. Then I still have my minus sine x, and it's all over h. My next step is going to be to group terms together. I'm going to take the sine x cos h and the minus sine x and put them together. And I'm going to treat that as one thing. And then I'm going to take the sine of h cos of x over h and put that together. And this leads to two difficult limits. So I'll give the limit to each piece. In this first piece, I'm going to factor out a sine of x. And that will leave me with this. And then the other piece, I'll bring out the cos x. Like this. The limit is as h goes to 0. So this sine x piece doesn't care about the limit, and this cos x piece doesn't care about the limit. So I can pop them out past the limits even. And you may remember back in the first week, I mentioned that the function sine x over x was going to be important at some point. Here is that moment. This is obviously not defined when h is equal to 0 because the bottom and top are both 0 there. This is also not defined when h is equal to 0 because cos of 0 is 1, so the top is 0 and the bottom is 0. So both of these limits require some special care. I'm going to tell you the result now, and then I'm going to show you why it's true. So, period. By work, I'll show you now, I'll show soon. the limit as h goes to 0 of sine h over h, this is 1. And the limit as h goes to 0 of cos h minus 1 over h, this is 0. So f primed of x is equal to sine x times 0 plus cos x times 1, which is just cos x. So, if you believe me that these limits are what I say they are, then this piece is 0 and this piece is 1. So this whole thing is sine x times 0 plus cos x times 1, which is just cos x. So the derivative of sine would be cosine. But it's going to take a little bit of convincing that this is 1. And then I can deduce from that that this is 0.
So any exam, we have to do it exactly by, like for each steps. Like let's say you put an example like that, we have to do it exactly like that.
I would not ask you on an exam to calculate the derivative of sine using the definition. So this is something that we're doing together, and I would not make you do exactly this on a test. If I asked you to calculate anything, any derivative using the definition, you would have to go through this procedure. And the example like we did at the start here, where we did little g primed, that would be a viable exam problem. But this one, because it involves so much kind of clever work using this identity and then splitting the limit up and then factoring, this I would not ask you to do on a test. But I do need you to think along with me because I want you to understand why the derivative of sine is cosine.
Right.
We're fairly convinced from this picture, I hope. All right, this, I mean, what else could this be? This got to be cosine, right? And that just comes from thinking about the slopes. So hopefully you're already convinced that the derivative of sine really is cosine. It doesn't just look a lot like cosine. There's only one thing that could be. But in this class, we do go through a few proofs, and this is one of them. So I don't expect you guys to reproduce this, but I do want you to understand it. So the last things we need to do here is show you that this limit is 1 and that this limit is 0. Here's the easy way. Let's look at decimals. Graph it as sine h over h. Doesn't want to let me do this. Okay, y equals, yeah, there it is. I'll rescale my y-axis. There it is. So here's sine h over h. As h goes to 0, clearly we're going to 1 from both sides, even though we're undefined at 0, right? We've got a little hole here. So the limit as h goes to 0, sine h over h really is 1. But the usual argument to show that involves some geometry. It's a squeeze theorem thing. So it's good practice. To show that lim h to 0, sine h over h equals 1, consider the diagram. This angle right here I'll call h. And then I can split this up into a few different regions. There's the area of the sector. Come in and shade this, let me see, like this. The orange area, the area of the sector, if this is the unit circle, then this radius is 1. The area of a sector of a circle, you know, the area of the whole circle is pi times r squared. So the area of half the circle would be pi over 2 times r squared. And in general, the area of a sector of a circle is 1/2 times the radius, which is 1 squared, times h or theta over 2. You can check that if you plug in 2 pi for h, that would be the area of the whole unit circle. You get 2 pi over 2, which is pi. Let me see. Oh, maybe this isn't necessary. Is it just pi times anything? Yeah, the 1/2 there isn't necessary. I got the other 1/2. So in general, it's r squared times theta over 2. That's the area of a sector of a circle. So here, if the angle is h, then the area of the sector is just h over 2, because we're on the unit circle. What about the area of these triangles? The small triangle in here and the big triangle here. So the area of the little triangle and the big triangle, let's see. So the area of the big triangle here, which I'll shade like this, right? So that's this guy. You can calculate using the formula for the area of any triangle. It's 1/2 times the base times the height. Well, that's 1/2 times the base here is the radius of the circle, right? Goes from the center all the way out to the edge. So that's 1, because we're on the unit circle. And then the height here, this point is cos h, comma sine h, because it's on the unit circle and the angle enclosed is h. So the height is the sine of h. Let's see, and then I think maybe the easiest way to do this, rather than considering the small triangle, would be to extend this guy all the way out here. So then I've got a big triangle. So this one will be the smaller triangle, sorry. There's another way to do this where you calculate the area of the little triangle in there. But this is, I think, a little bit easier for most folks. How can we sort out the area of this bigger triangle? Well, that's still 1/2 times the base times the height. The base is still 1. But what's the height of this triangle? Well, it's a similar triangle to the little guy, and the little guy in here has height sine and base cosine. So this big guy has to share the same ratio of side lengths. So that height is actually the tangent of h. And then we make an inclusion argument. So the purple triangle this triangle is definitely the smallest of the three shapes. The purple triangle is contained in the sector, and then the sector is contained in the big triangle. So by inclusion, what I mean is that the purple triangle is included in the sector. So the area of the purple triangle is less than the area of the sector. So the area of the small triangle is less than or equal to the area of the sector is less than or equal to the area of the big triangle. And now I plug in for each of these, and I'll get something to which I can apply the squeeze theorem. The area of the small triangle is 1/2 sine h. The area of the sector is h/2, or 1/2 h. And the area of the big triangle is 1/2 times the tangent of h, or 1/2 times sine h over cos h. If I divide everywhere by the sine of h, by 1/2 times the sine of h, then I'll get 1 is less than or equal to h over sine h is less than or equal to 1 over cos h. Now I can take the limit as h goes to 0 everywhere. This is 1. And as h goes to 0, cos h goes to 1. Because cosine of 0 is 1, it's continuous there. Therefore, by the squeeze theorem, the limit as h goes to 0 of h over sine h has to be 1. And if h over sine h goes to 1, then so does sine h over h. If your reciprocal goes to 1, so do you. And that's the proof. So really it is true that the limit as h goes to 0, sine h over h is equal to 1. To finish things off, I would have to show that the limit as h goes to 0 of 1 minus cos h over h is also 1. I'm going to leave that as an exercise for you. Use this fact that lim h to 0 sine h over h equals 1 to prove that the limit h to 0 cos h minus 1 over h is 0. I'll give you a hint. You want to multiply by cos h plus 1 over cos h plus 1. That'll give you cos squared minus 1 upstairs. That you can rewrite in terms of sine, and then you can use this. So the upshot here I'll leave this down here. So use the fact that limit h to 0 sine h over 1 is 1 to prove that the limit as h goes to 0 of cos h minus 1 over h is 0. It's not terribly hard. And once you have that, you have the derivative of sine. So now we know that the derivative of sine really is cosine. A similar argument will show that the derivative of cosine is negative sine. So these are some of the reasons why mathematicians love sine and cosine so much. Their derivatives kind of bounce back and forth in this really neat way. And that's a useful fact in so many different senses. I think we're going to have to stop here. Let me give you the other trig derivatives. And then on Monday, sorry, what's today? Today's Wednesday, right? So on Friday, then I'll walk you through the procedure for cooking up the other ones. I appreciate you guys being patient with me. So sine differentiates to cosine, cosine differentiates to negative sine. If you want to find the derivative of tangent, you rewrite it as sine over cosine and then use the quotient rule. It turns out to be secant squared. The derivative of secant turns out to be secant times tangent. The derivative of cosecant is negative cosecant cotangent. And the derivative of cotangent is, following the same sort of pattern, negative cosecant squared. So these are the derivatives of all 6 trig functions. It's a little bit of work to cook them up using the definition, but once you have the derivative of sine and the derivative of cosine, all the other guys follow by a mixture of quotient or product rules. Actually, just quotient rules. A common exercise on my exam 1 is to cook up one of these using the quotient rule. So you really do need to go through this process. I'll do at least the first 2 for you guys on Friday. And then we'll get some practice using these together with the product and quotient rules to solve the remaining homework problems for homework 5. So this is where we got to leave it today. I got another class to get to. I appreciate you guys hanging around and being patient. Again, you can take your time and figure out this limit a handful of different ways, but the argument I gave you using area inclusion is my favorite. If you look in the modules, I do think I have a link to that argument if you want to go through it more carefully. But for your purposes, what you really need to remember are these derivatives. All right, so make sure you're getting lots of practice with product and quotient rule. Remember the derivatives of the trig functions and then get to work on those remaining homework problems. We'll talk more on Friday. All right, take care, guys.
Thank you.